Okay, good morning, everyone. So I'm Thomas Vidick. I was the chair of the PC for ITCS, and I'm honored to also chair the first session, which is a great ITCS session. So I put up the titles of the papers that are going to be in this session up there. So it's a very diverse session around algorithms, but some of these are upper bounds, some of these are lower bounds, some of these are connections. But as I was preparing for this and looking at the comments that the papers received, one thing that unites almost all of them is simplicity. And so a lot of the reviews on these papers commented on the elegance and the simplicity of the reduction or the algorithmic results that are given. So we're going to start by a paper by Alman and Williams on fine-grained complexity. So what they do is show that for many simple graph algorithms, but not all, such as, for example, finding triangles or more generally k-cycles for k bigger than 3, then the fine-grained complexity of these problems reduces to their fine-grained complexity on a special family of graphs called orthogonal vector graphs that have some kind of interesting structure, low-dimensional structure. So Josh is going to tell us about that result. Second result is by Connor, Landsberg, Gesmundo, and Ventura, and Joseph will give the talk. And these are following this long line of works trying to obtain upper bounds on the matrix multiplication exponent. So I don't think they get any new upper bound, but they study a family of tensors that was introduced by Coppersmith and Vinograd, which is sort of the most promising family of tensors for obtaining lower bounds. And they prove some positive and some negative results about these tensors. Then we have a very nice result by Kai and Hovarau that revisits an old theorem by Lov'asz from the 60s that shows that the function that's up there characterizes the isomorphism type of the graph H, that's a fixed graph H there. But they generalize this to not only regular graphs, but graphs that have weights on the vertices and the edges. And they also give a simpler proof of Lov'asz's result. And one of the nice consequences of their generalization is that it allows them to obtain constructive algorithms, so as a consequence of having a simpler reduction or proof of the result. The next result is by Ramamoorthy and Rashtchian, and I guess I wrote it's in the title, so you can read the title. So they show an equivalence between certain data structures and the matrix rigidity problem. They tell you about that. One of the nice things about their result is that it's a connection, and people always get excited by connections, and I think it's justifiably so. But they get something out of it. So they actually get some new query lower bounds for certain data structures based on importing matrix rigidity results. Okay, two more, I think. Second to last presentation is by Lincoln, Polak, and Williams. And this is again about fine-grained complexity. So they study sort of the whole landscape of matrix multiplication or convolution problems. So these are always based on a certain ring. And there's many possible rings. So plus multiplication is or maybe it's multiplication addition will be regular matrix multiplication, but then you have min-max ring, min-plus ring, many such rings. And depending on how you change the ring, the fine-grained complexity of the problem changes. Could be matrix multiplication, could be n squared, could be n to the 1.5. And so they establish a lot of very clean reductions between many such problems that relates their complexity in a sharp way, assuming complexity theoretic, making complexity theoretic assumptions. And then the last paper is by Anari and Vazirani. And they sort of revisit the planar matching problem in general graphs. So prior to their work in the past maybe 3 or 4 years, it was shown that the planar matching problem for general graphs is in NC, and there's a relatively involved algorithm that's given by these authors, building on work of others for the problem. What they do in this paper is that they rederive a different algorithm for the same problem in arguably a more natural way. So they get a cleaner, simpler algorithm that's obtained by giving a search to decision reduction for the problem. So the fact that the decision perfect matching problem was in NC was known before. And so here they derived the search, the algorithmic result from it. Okay, so I've talked enough. So first talk is by Josh Alman, and he's going to tell us about, oh, and I lost the mic, no, about OVA graphs.
Okay, hello. Yeah, I'm Josh. So today I'm going to tell you about why OV graphs are probably hard instances of a lot of different graph problems. And this is joint work with Vassilevska Williams. Okay, so first of all, what's an OV graph? Oh, okay. So OV graphs are sort of defined or inspired by the orthogonal vectors or OV problem. So in this problem, it's a really important problem in fine-grained complexity, as I'll talk about in a couple slides. So in this problem, you're given as input n vectors, and these are vectors of 0, 1s of dimension d. And usually think of d as like order log n. And your goal is to figure out whether or not there's a pair of vectors that are orthogonal to each other. So their inner product is 0, but not like over f2, over the integers. So you're trying to figure out, is there a pair of vectors such that in each entry, at least one of them is 0 in that entry. Okay, so this is the orthogonal vectors problem. And then an OV graph is like a graph inspired by this problem. So for n vectors that are 0, 1 vectors, again, you can think of an n-node graph where the ith and jth nodes are adjacent if and only if the corresponding vectors are orthogonal. That's an OV graph. And then given an OV graph, you can sort of naturally define lots of different algorithmic problems, like the analog of all sorts of different graph problems that we normally study. You can also ask them just about OV graphs. So where you're given as input, instead of just any n-squared edge graph, you're given as input the n vectors defining an OV graph. Then you can ask, oh, for example, the OV question itself asks, like, does G have any edges? And then you could ask the OV triangle question, does G contain a triangle? Or max clique, what's the biggest clique in G? Directed K cycle, you can direct the edges in some way and ask, is there a K cycle in this graph, and so on. So you can ask, like, for any basic algorithms questions you can ask about general graphs, you can ask them about OV graphs as well. And that's what we study. So let me tell you a little bit more about OV. And probably the reason that it's studied so often in our community is because of this nice result by Williams from 2005, where he showed that faster algorithms for OV would lead to breakthroughs for solving SAT. So OV, you can solve it in quadratic, like roughly quadratic time by just checking each pair of vectors and seeing if they're orthogonal or not. And Ryan showed that if you could do substantially faster than that, it would actually lead to big breakthrough algorithms for SAT. So let me be a bit more precise. So normally we give this so-called OV conjecture that it says this, like for any epsilon, there's a big enough C so that in dimension C log n, it requires n to the 2 minus epsilon time to solve the orthogonal vectors problem. And then, and our known algorithms don't break this conjecture. And then Ryan related it to the strong exponential time hypothesis, which looks in structure very similar, is that for any epsilon, there's a big enough k such that k-sat requires time 2 to the 1 minus epsilon times n. And what Ryan showed is that the strong ETH implies the orthogonal vectors conjecture. And this is like the foundation of a lot of fine-grained complexity. A lot of it is built off of showing that the orthogonal vectors conjecture then shows tight hardness for a bunch of different algorithmic problems as well. So what we prove in this paper is kind of an analogy of this result, but for lots of different OV graph problems instead of just OV. So the problem we get a breakthrough for is a little bit different. Instead of SAT, it's Maxat. But then what we show is that for lots of different problems, like finding triangles in OV graphs, finding directed cycles in OV graphs, solving a lot of different dynamic graph problems in OV graphs, and so on, if you could solve these faster, it would lead to breakthrough new algorithms for Maxat. And by faster, I actually mean faster than the known algorithms for general graphs. So if you could solve these problems on OV graphs of low dimension faster than like the best known algorithms for solving them on general input graphs, it would actually lead to breakthroughs for Maxat. Okay, so let me tell you a little bit about Maxat a little bit more. So Maxat, probably you've all seen this problem before. In max ksat, you're given a KCNF formula with n variables, and you want to figure out the maximum number of clauses you can satisfy with one assignment. So what's known about it? So for max 2sat, so you probably know 2sat, like the usual 2sat problem you can solve in polynomial time. Max 2sat we don't know how to do that. And the best known algorithm looks like this. It's n to the omega times n over 3 is the best running time, where omega is the matrix multiplication exponent. And this was a nice result by also Ryan from 15 years ago. But for max ksat for any k bigger than 2, we actually don't know any, we basically don't know any non-trivial algorithms. The best running time is, there's no n to the 1.99 to the n algorithm even for max 3 sat. And these are even the best known algorithms for sparse instances of Maxat with just order n clauses. So normally with SAT, there's nice sparsification lemmas that you can assume you don't have too many clauses. Those don't actually work out as far as we know for Maxat, but even if you restrict to these sparse instances, these are still the best known algorithms. So these have been standing for 15 years or more, and sort of the assumption we make to justify our claim that OV graphs are hard instances is that you can't improve substantially on these. So either OV graphs are hard instances of these graph problems, or else you can improve on these long-standing running times for Maxat. Okay, so let me more precisely state the result, at least for triangle finding. So for triangle finding, the best known algorithm to find triangles in general graphs runs in n to the omega time. Again, omega is the matrix multiplication exponent. Probably many of you have seen this before. You basically just square or cube the adjacency matrix of the graph, and then you can use that to figure out whether the graph has triangles or not. So here's our new theorem. What we show is that if you can find triangles in n-node OV graphs of dimension only order log n, so you're given as input just n vectors of dimension log n, and you want to figure out whether this graph has a triangle or not, then if you can solve this in better than n to the omega time, like n to the omega minus delta time, then you can solve sparse max 2 sat instances faster in time 2 to the omega over 3 minus delta times n. So if you get a savings for finding triangles in these just OV graphs of dimension order log n, then you get a corresponding saving for solving max 2 sat as well. And yeah, one thing I think that's really neat about this is that to solve OV triangle finding, so it suffices again to square the adjacency matrix of an OV graph. So in particular, this reduces to some really nice natural matrix multiplication problem, where there's this class of only 2 to the order n log n different matrices that we want to be able to multiply or square. And if we can just multiply or square these matrices faster than we can multiply general matrices, of which there are a lot more, like 2 to the n squared, then that would lead to faster algorithms for max 2 sat and so on. And then in addition to this, we also prove similar results for OV-directed k-cycles. We show hardness like this from max 2 sat, a similar kind of hardness result from max k-sat for any k. So in fine-grained complexity, triangle finding is already sort of known to be related to lots of different dynamic problems. So we also sort of almost as a direct consequence of this show hardness for a lot of dynamic graph problems where you get dynamic updates where you update an entry of one of the vectors defining your OV graph, something like this. But yeah, you can see the paper for more details about that. So the last question I want to quickly talk about is whether or not all problems are hard on OV graphs, right? So I gave a few examples of problems that seem to be just as hard on OV graphs as in general graphs. And we actually even show more results along these lines. So for example, we show that any problem that's NP hard on sparse graphs is also NP hard on OV graphs of dimension just log n. So the Hamiltonian path problem and the vertex cover problem and so on are still NP hard on this small class of graphs. But we do give, as Thomas mentioned, we do give some examples of problems that you can solve faster on OV graphs. So one example is that max clique in OV graphs of dimension d, you can solve it in 2 to the d times polynomial in n time. So when d is small enough, you can solve this faster. This actually is a very simple reduction to known fixed parameter tractable algorithms. We also give a faster algorithm for a problem that's related to triangle finding called online matrix vector multiplication. So here the goal is you're given as input, let's say a graph, and you want to pre-process it so that when you're given a vector, you can quickly multiply the adjacency matrix of the graph times the vector faster than just like the trivial way to do it. And we also show if the graph is an OV graph of small enough dimension, then there's a nice way to decompose the matrix in pre-processing so that you can solve this type of problem faster. Yeah, so there are some problems you can solve faster in OV graphs, and we give some algorithmic ideas in our paper, but it would be really interesting to figure out whether it's possible for like triangle detection and stuff like that too. Okay, yeah, that's all I have to say. Thanks.
So we have plenty of time for questions.
Can you just say what any problem that is NP hard means? Like, do you show a general result for NP hard sparse graph problems?
So basically, we show like a polynomial time deterministic algorithm for taking in as input a sparse graph and outputting like vectors of dimension log n that define it as an OV graph. So if you could solve it in these OV graph, you could like, yeah, that just immediately implies this.
Other questions? Okay. Let's thank Josh again.
Maybe.
Did you press the, like there's a button sometimes you press to like switch the, like this thing?
I don't know. That's
Okay.
why I need help.
It's your computer, no?
What?
It's your computer?
This is my computer, yes.
Okay. Oops.
Someone did this for me earlier this morning, and it worked.
How do you switch, this is a MacBook Pro, I don't know how to use this thing. How do you
Yeah, I just
get the projector?
still haven't figured this out.
Cheyenne, do you use a Mac?
You did this for me, and you told me it would be automatic.
What is the problem? Oh, no, I know what happened because the thing is unplugged.
Oh, that is not my fault.
Because we use that. Yeah, it's not your fault.
Wait. Is it working? It's still not working?
Yeah, you're getting there. It's coming.
Okay.
And then that part you know how to do.
Okay.
Okay, great. So the next talk is going to be given by Joseph Landsberg on tensors not subject to barriers for Strassen's laser method.
Okay, so let's just get straight to the punchline. Let's take a 3x3 matrix, take its determinant. That's a polynomial in 9 variables, but I want to think of it as a tensor. Do the same thing for the permanent. So we think of them as tensors rather than polynomials. And either of these tensors could be potentially used in Strassen's laser method to prove that the exponent of matrix multiplication is 2. That is, as your matrices get large, it gets almost as easy to multiply them as it is to add them together. And what we're also going to report on is what is this theorem saying, and then some good news and some bad news. Maybe, well, it depends whether you're trying to prove exponent is 2 or less than 2.3 or not. So there is good and bad news either way. It just, depending on your ideology, you may have different point of view, which is the good and which is the bad. Okay, so let's get going. I need to phrase things in the language of tensors. So when you multiply two matrices, you eat a matrix, you eat a second matrix, you spits out a third. That's a bilinear map. We want to view it as a trilinear form. That is, you eat 3 matrices and spit out the trace of their product. And so we view matrix multiplication as a point in this tensor space. And this is the framework in which most lower and upper bounds for matrix multiplication are proven in this tensor language. So tensor has rank 1, just like if a matrix has rank 1, you can write it as a product of a row vector and a column vector. Same thing here, only you need 3 vectors. And the rank is the smallest r, such that you can write your tensor as a sum of r rank 1 tensors. If you have a tensor, now this is new to tensors, doesn't happen with matrices, is rank is not semi-continuous. So there's this notion of border rank, which is the smallest r such that the tensor is a limit of tensors of rank r. And these are different notions in the tensor world. They're the same for matrices. And Strassen and Bini proved that this is a valid way to study the exponent of matrix multiplication. So this tensor language is an appropriate language for studying exponent of matrix multiplication. You fix your, you allow your size of matrices to grow. You look at this function, this border rank function as a function of n. The growth of this function determines the exponent of matrix multiplication. Now, matrix multiplication tensor, all as beautiful as it is somehow too complicated for people to deal with. So most research on upper bounds since 1981 has been very indirect, uses other tensors than the matrix multiplication tensor. So let me explain briefly how that works. If you are given, somebody hands you a tensor, you can form a much larger 3-way tensor by just tensoring it up as some enormous tensor and then crushing it down so that it's living in product of 3 spaces again. This is called the Kronecker power. The matrix multiplication tensor has this remarkable self-reproducing property. Normally, if you take a Kronecker square of a tensor, you get a new tensor that has nothing to do with your old one. It has completely different behavior. But here, you input matrix multiplication, you raise it to a power, you get a big matrix multiplication out. And this is essential to all the upper bounds research since 1981. So in particular, you can upper bound the exponent using any fixed n and high powers of a fixed, say, 2x2 matrix multiplication tensor. So you just need to work with one small tensor, but some asymptotic property of that small tensor. And this Strassen's laser method says, like I indicated earlier, instead of using matrix multiplication itself, you take other tensors that you think you understand better than matrix multiplication, and then you sort of take some gigantic power and then you degenerate them to something that has matrix multiplication inside to get an upper bound on the exponent. I'll give you an explicit example later in the talk. And there is the most famous tensor for this method, the so-called big Coppersmith-Vinograd tensor, and that has been used to prove the world record. It proved the world record in 1988, then nothing happened for 20 years, and then it proved the new world record, which is like almost a 3-way tie, moving that last 8 down to 7-3. Now, then in 2014, there was some bad news from Avenus, Filmus, and Legal. Game is essentially over for the big Coppersmith-Vinograd tensor. You cannot prove anything better than omega less than 2.3 using the big Coppersmith-Vinograd tensor. Okay, so that leads us to a challenge. Find other tensors that can prove better upper bounds on the exponent using this so-called laser method. Okay, so before the big Coppersmith-Vinograd tensor, there was a little Coppersmith-Vinograd tensor that's a little bit, disconnected. Okay, we have a problem. What do you mean it's okay? There it is. Okay. So before the big Coppersmith-Vinograd tensor, there was this simple-looking tensor. For each, it's defined for every q greater than 1. It's interesting. It looks quite easy to write down as a tensor. And you can see with these manipulations that you can get upper bounds on the exponent. And you get pretty close to the world record. I didn't touch anything. Something Okay, I'm not touching anything. I'm being very careful not to touch anything. And it's back. Okay. And I'm really keeping my distance. So this simple, very simple looking tensor was proved. Now, its border rank is q plus 2. It could have been q plus 1, but it's not. And you get that the exponent is less than 2.41 using this when you plug in q equals 8 and k equals 1. And that was, for a little while, the world record. But notice that if sort of as k went to infinity, already for this CW2, which is a very tiny tensor, if that 4 went down to a 3, that would imply that the exponent is 2. So it's ever since the 80s, they asked this very natural question, does this thing drop rank when you take Kronecker powers? And that question was around since 1988, so Blazer said, okay, let's be more modest. Let's just ask when we square it. Okay, so now for those of you who want to lower the exponent, I will present you some bad news. The first theorem is it squares, the worst possible result. And almost worst possible result for that little one. I think we're going to resolve that someday soonish. We have a method to do that, but I don't have time to discuss the methods, and you wouldn't want to hear about them today anyway. So that's unfortunate, and even worse news is when you cube it, you still have bad news. Except you notice there's a little bit of optimism because the cube one, you have to have q greater than 4 rather than q greater than 3. So there's a little bit of kind of wiggle room maybe possible there. Okay, so that's the bad news. Now, let me try to give you some good news for upper bands fans. So we spent, how much time do I have? Time? No one's telling me. 3 minutes. So we spent some time looking for new tensors. I'll explain how we look for them in a moment. But one of them we found is a sort of skew-symmetric cousin of the Coppersmith-Vinograd tensor. I'll make that precise in a moment. That has the exact same behavior for upper bounds on the exponent. So, as Josh and Williams can tell you, these things are dime a dozen, but I think this one is a little special, and I'll explain why. But first, a little bit of bad news. It's even worse than the little Coppersmith-Vinograd tensor, in the sense that the Coppersmith-Vinograd tensor had q plus 2, and here we have something worse than q plus 2. For example, it's q plus 3 when q is 2, which is 5, which is greater than 4. So it is not looking good, this tensor at first. And now one piece of good news. When you square this one, though, oh, yeah, and like I said, it has the same behavior as Coppersmith-Vinograd. When you square it, you get a drop. And so this drop is very promising. And we had predicted this drop would occur based on geometric considerations that I'll describe in a moment. And if this drop continues, it would be very good news indeed for the exponent. So now let me tell you where this thing came from and why we have high hopes for it from geometry. So our approach to this AFL challenge to find new tensors for Strassen's laser method was to study these tensors not as combinatorial objects, but as geometric objects, and look for other tensors with similar geometric features. And an interesting feature of all the Coppersmith-Vinograd tensors is they have large symmetry group. The orthogonal group, the group of rotations, is the symmetry group for the little Coppersmith-Vinograd. This new tensor has a bigger symmetry group. The sort of what's bigger than the orthogonal group is the symplectic group. The group preserving a skew-symmetric form is bigger than the group preserving a symmetric form. This is how we found it from geometry, and this is what makes us hopeful that when we take its powers, it will give us interesting results. Now, I have to get back to the beginning of the talk. For both the skew Coppersmith-Vinograd tensor and the standard one, when you square them, you get something you knew from the get-go, a very familiar polynomials, which we consider as tensors that I started the talk with. And that also opens up new paths to studying both of these tensors. I thank you for your attention.
Questions for the speaker? I had sort of one very naive question, which is related to one of the later talks. So you stated everything over the complex numbers. So how robust are these things to? I mean, I assume the reals would be the same, but how about finite fields, or does it completely change, or?
As far as I know, so if the Coppersmith-Vinograd upper bound on the exponent is the same over finite fields, then this is the same. It's the same methods. And the symmetry group, of course, changes over finite fields, but you still have this symplectic group over finite fields and this orthogonal group over finite fields. They look different.
Oh, so any bound that you could prove on the rank for the tensor over whatever the field you choose, this is going to extend to the other fields?
If the laser method works over that field, and that I'm not sure, then the answer is yes. There's nothing particular to complex numbers about our work, but the work we rely on, it may be.
Okay.
So you showed the example with these two tensors that your new one corresponds to determinant over 3 by 3 matrices. Permanent is, the Coppersmith-Winograd one is permanent. Are there similar?
The squares of those.
The squares of those, sorry, yeah. Are there similar analogs with larger numbers than 3 or?
So you get some interesting things, but they're not familiar. They're new tensors, and I think they're quite exciting. See, because when the skew Coppersmith-Vinograd tensor is not symmetric, the Coppersmith-Vinograd tensors are symmetric tensors. They could be viewed as polynomials. Our skew guys cannot. But when you square something skew symmetric, you get something symmetric. And so we get new interesting polynomials, and that is very much work in progress, understanding these higher Q ones.
Okay, let's thank the speaker again. Talk is going to be given by Artsiom Hovarau on a theorem of Lov'asz that some function determines the isomorphism type of H.
So graph homomorphism has been an active research area for more than a half. Okay. So graph homomorphism has been an active research area for more than a half century. So it is a framework that can encode a wide variety of graph properties. So the definition is given as follows. Here, phi is a map from virtues of G to virtues of H, sometimes called colors. It is a sum of product computation. So by definition, the sum has exponentially many terms. So notice if the vertex weights alphas are 0, 1, and the edge weights betas are, if the vertex weights alphas are 1 and the edge weights betas are 0, 1, then the sum hom counts the number of maps that map edges of G to edges of H. So now this definition, this is called the unweighted case. So the left-hand side graph G can have multiple edges but no loops. This function hom is called the partition function of graph homomorphism. So in that paper of 1967, Lov'asz shows that if two unweighted simple graphs define the same function hom, then they are isomorphic. So here, simple means without multi-edges, but possibly with loops. So again, it corresponds to the unweighted case, and this unweighted case has 0, 1 edge weights and no vertex weights. That's all vertices have weight 1. So, okay. So many combinatorial problems. Many combinatorial problems can be expressed as graph homomorphisms. So this include vertex cover, independent set, and vertex covering. In all these, the vertex weights alphas are 1, and the edge weights betas are 0, 1. Less obvious is that the function that corresponds to counting the number of even and odd induced subgraphs in a graph is also expressible as graph homomorphism. So there are numerous problems coming from statistical physics, which include, as it has special cases of graph homomorphisms, which include the Ising model, the Potts model, the hardcore gas model, the Widal-Rawlinson model, and many others, but we will not talk about this in our presentation. So in complexity theory for exact counting of graph homomorphisms, complexity dichotomies have been shown. It's either the problem is sharply hard or computable in polynomial time, that is tractable. Assume the right-hand side graphs are only edge-weighted. So it's convenient to identify an edge-weighted graph with the corresponding symmetric matrix of edge weights. So for a symmetric matrix A, the following is the definition of the problem ideal of A. So there is a long sequence of studies by many researchers about the complexity of counting the partition function of graph homomorphisms. This range from the 0, 1 edge-weighted to the complex edge-weighted case. So allowing the matrix A to be non-symmetric corresponds to the case of directed graph homomorphisms, for which we have the following dichotomies. So, okay, for the weighted case in 2006, Lov'asz shows that if two twin-free graphs with positive vertex and real edge weights have the same function hom, then they are isomorphic. So we remark that the condition twin-freeness to be defined later is necessary. Otherwise, it's easy to construct a counterexample. So another interesting question is the expressibility of graph parameters as graph homomorphism. So an explicit expressibility criterion for graph homomorphisms with positive vertex and real edge weights was obtained by Friedman, Lov'asz, and Scriber in 2007. So it was subsequently extended by Tsai and me to account for vertex and edge weights from an arbitrary field without any restrictions on them. So these results are all carried out in the framework of label graphs. In order to understand the results, we need to give a few definitions first, with the first one being that of a label graph. So a k-label graph is a graph in which some k nodes are labeled by the numbers from 1 to k. So the product of k-labels graphs is the graph obtained by taking the disjoint union and then identifying the nodes with the same label. Okay, so next we define a simple label graph. It's the underlying graph is simple and no edges between the labeled vertices. Again, note that the graph G1, G2 from the previous slide are not simple as two label graphs according to our definition because of the edges between the labeled vertices. So on the other hand, even the product of two simple label graphs is a simple label graph, which is illustrated by the graph G3 and G4. Okay, so next we define an F-weighted graph. We assume by default that the vertex weights alphas are non-zero because zero vertex weights don't give any contribution to the partition function, and so they can be freely removed. So after that, we define a partial graph homomorphism function, and we know that the function hom can be expressed as a linear combination of such functions. So now, next, we need the notion of twin vertices in a graph. So we know that for unweighted graphs, for undirected graphs, we only need one set of equations. For example, the first one. So for undirected, unweighted graphs, twins are any two vertices with the same neighbor set. So it's also natural to define the twin compression step as follows: we combine two twin vertices into one supervertex and take the sum of the vertex weights as a weight of the supervertex. And if the sum is 0, then remove it. And so it's easy to see that this step doesn't change the partition function. Okay, so with that said, we can proceed to Lov'asz result. He shows that if one restricts consideration to positive vertex and real edge weights, then the partial graph homomorphism function uniquely determines the right-hand side graph up to a label preserving isomorphism. So in this theorem, the statement is formulated for undirected graphs. So the next result is due to Scriber. Namely, his results deals with partition functions of graph homomorphisms for complex edge-weighted graphs, but no vertex weights. However, in his paper, he uses a bit different framework. In particular, he allows left-hand side graphs to have multi-loops, and this particular result is formulated and shown only for unlabeled graphs and doesn't generalize to labeled ones from his proof. And so the results by Lov'asz and Scriver are incomparable. And finally, Rex, in his PhD thesis, proved a version of Lov'asz statement for arbitrary weights from a field of characteristic 0, but he also allowed left-hand side graphs to have multi-loops in addition to multi-edges. Okay, so in the papers by Friedman, Lov'asz, Scriver, 2007, Lov'asz, 2006, and Scriver, 2009, very sophisticated tools were developed. In particular, the algebra of quantum graphs originating from labeled graphs. In this paper, we found a particularly elementary method we call the Vandermonde argument to give a full generalization, unifying all the previous similar statements. So the following is our result. Roughly, it says that a partial graph homomorphism function uniquely determines the right-hand side graph up to a label preserving isomorphism. A bit more general, though a bit more technical main theorem can be found in the proceedings. So we note the following. It works for both directed and undirected graphs, works for an arbitrary field of characteristic 0, which includes complex numbers, and we only need to consider simple k-labeled left-hand side graphs. So as noted earlier, twin inference is a restriction that's necessary. There are easy counterexamples. Characteristic 0 is also necessary. We constructed a counterexample for any field of finite characteristic in the proceedings. So pursuing an idea mentioned in a footnote in a paper by Godler, Rex, and Vena, a vehicle version of our theorem can be proved. This idea is described in our paper in the proceedings. The interested readers are encouraged to look at it. So restricting our result to 0 labeled graphs, we get that every twin weighted graph is uniquely determined up to an isomorphism by its function home. So now let's proceed to the outline of the main proof. So as mentioned before we introduced a very simple argument that we call the Vandermonde argument. So for example, working over the complex numbers and assuming that equation 1 holds, we can conclude that the following combination of conjugates is 0. However, the actual version that's used in the paper is a multi-dimensional version of this argument and is achieved by iteratively applying the one-dimensional version. So now we proceed to the actual outline of the main proof. So we work in the framework established in Lov'asz paper. Our main proof is partitioned into 2 parts. In part 1, what we do is to prove our main theorem, but assuming that one map, say phi, is highly surjective, that the preimage of any point has large cardinality. The exact bound is included in the corresponding statement. So in our proof, we first construct 2 finite families of simple label graphs. These graphs are precisely described in the proceedings. We evaluate the given partial graph homomorphism functions at them. The high surjectivity ensures that we get expressions for which we can apply the Vandermonde argument. This is done multiple times. So next, in part 2, we proceed to the proof of the main theorem. This time, we don't have any high surjectivity requirement. However, what we can do is extend one map, say phi, to be highly surjective and expand the given equality of the partial graph homomorphism functions along the newly introduced L minus K labels. The left-hand side graphs that we use here are products of the graphs from part 1, but they are labeled this time. By noting that partial graph homomorphism functions are multiplicative, we can apply the Vandermonde argument, again. So, and the conclusion is that there is another map extending psi and a graph isomorphism, sending the first extended map to the second one. So our proof actually produces an explicit finite family of simple labeled graphs. We call them witnesses, such that one of them will separate phi and psi in case the maps are not equivalent. The number of witnesses to check is double exponential in the combined size of h, h prime, and k. So thus our proof is fully constructive. This is a difference from Lov'asz proof because his approach does not give us a time bound to find a separating witness. So in case of non-equivalence, this may require an open-ended search. So we don't know when to stop. So, okay. Now we proceed to the finally. Okay, yeah, okay. Finally, we proceed to the applications to complexity theory. So for counting graph homomorphisms for undirected graphs with complex edge-weighted graphs, we have a dichotomy due to Tsai, Chen, and Liu. So the paper itself is very long. It's over 100 pages of proofs, and the tractability criterion is technically complicated. It is known that the dichotomy is decidable in polynomial time in the size of A. That is, given a matrix A, we can decide in time polynomial in the size of A, whether eval of A is a polynomial time solvable problem or sharply hard. Recall that for the eval problem, the input is a graph G, and the complexity time bounds are measured in its size. However, in case of Sharpe hardness, the proof does not produce a reduction from some canonical Sharpe hard problem, for example, the permanent, to eval of A constructively. That is, on input a matrix A, such that eval of A is Sharpe hard. In other words, uniformly in such Sharpe hard matrices A. So now, our main theorem and a few other technical adjustments can actually make the dichotomy fully constructive in this sense. Okay, so, and that completes my presentation. Thanks. Any questions?
It's time for a question.
Thomas, you can ask me a question. If you have a question, you can ask me.
I don't.
Oh, okay.
Okay, if there's no question, let's thank the speaker again. So then, oh, so we messed it up. Okay. Okay, so the next talk is going to be given by Sivaramakrishnan on the equivalence of systematic linear data structures and matrix rigidity.
Thanks. Yeah, so this is joint work with Cyrus Rashtchian, who's in the audience. So let me start. So circuits and data structures are two very important models of computation. And this talk is about establishing or showing a connection between the two, okay? And the key motivation or the starting point for our work is, yeah. You need to be pretty close. Okay. Is it better now? Yeah, okay, perfect, yeah. No, I think this is good, yeah. Perfect, so, the key motivation for this talk is a bunch of recent works where they show that if you prove new data structure load bonds, then you'll be getting new circuit load bonds. For example, the work of Devir, Golovnov, and Weinstein, they show that if you prove load bonds against linear data structures that compute inner products, then you'll get new rigidity load bonds, okay? And in this work, what we show is that the notion of rectangular rigidity is equivalent to systematic linear data structures. And that's the first result of this work. And before I actually state it formally, I'm going to define rectangular rigidity and also define the systematic linear data structure model. Okay, good. So let's get started. So, good. So this notion of rectangular rigidity was introduced by Alman, Panigrahi, and Ekanen, which is kind of, you can think of it as a generalization of Valiant's notion of rigidity. What they ask for is a subset of vertices in F2 to the n that has the property that like these points are somehow far away from any low-dimensional subspace. Okay, so usually for such structures, if you just pick a random subset of F2 to the n of appropriate size, you'll see that they are rigid or like they have these nice properties. And in this talk, what we're really interested in is like explicit sets in the sense that you can like there's a polynomial algorithm that will actually output all these points in the set. Okay, so now say like what do I mean by not they're far away from any low-dimensional subspace. What I mean is if you actually write down a matrix that corresponds to this set Q, where each row corresponds to a point in this set, what I claim is, or what we want is that you cannot express this as a sum of low rank matrix plus sparse matrix. And the notion of sparsity here is that each row, it's a row sparsity instead of the sparsity of the whole matrix. Okay, so the difference between this notion and the notion that Valiant had was that in the case of Valiant here, the size of the set would exactly be equal to n, which is the dimension of the space. And also, instead of looking at row sparsity, he looked at the sparsity of the whole matrix. Okay, so that's the difference. And formally, what we want is we call a set RT rigid if for every r-dimensional subspace V, there's a point in the set that's at a Hamming distance of at least t from V. Okay, so this matrix that corresponds to the set, if you write it down, you cannot express it as a sum of a rank R matrix A plus a matrix B that is T sparse. Okay, is the definition clear? Any questions at this point?
So what's the motivation for considering sparse rows as opposed to just sparseness?
Okay, so I feel like this. Okay, so this is in one way can be thought of as a generalization of like what, or like a relaxation of what Valiant asked, where instead of looking at the sparsity of the whole thing, you just ask for one row. Geometrically, you can think of it as you have all these points in F2 to the n, and you want at least one point to be far away from the subspace you're looking at. Instead of saying that the average distance of all the points from the subspace is large, all you want is at least one point to be far away. It's just like worst case versus average. Yeah. And I like to think of it in the geometric way instead of just matrix. Yeah. Yeah. Okay. Perfect. Any more questions at this point? Good. Okay. And okay. So what we want for this question is that we want to be able to produce explicit sets Q, and want to be able to understand the relationship between R, T, N, and the size of Q. Okay. For instance, if you pick an n square size set at random, then it will be rigid with parameters T being at least omega n over log n, for R being even n over 100 and something. Like even if you look at like distance from n over 100 dimensional subspaces, you still get n over log n as like the distance. Okay, but then the best known explicit lower bounds for this are of the form where T is at least n over R times log size of Q over R, where T is the sparsity parameter and R is the rank parameter. Okay, and good. So I'll move on to now define the systematic linear model. So here the goal is to store a vector x in F2 to the n and be able to compute inner product queries of the form Q times x, where Q is from the set capital Q. Okay, and now let me tell you how the set is stored. All you do is you write down x first, and then you write down R more inner products with arbitrary vectors a1 through ar. Okay, so this is all you get to store. And so this accounts to n plus r bits. And then for the query, what you do is you actually access a subset of these bits to be able to output the inner product. Okay, so is the model clear? And here two parameters that we're interested in are like the number of redundant bits that you store, and the query time, which is the number of accesses to just x and not the redundant bits. Okay, so the number of accesses that you get charged for are the number of accesses to x and not the redundant bits that you store. Okay, good. Any questions about this model? Good. Okay, so now let me tell you how to get an upper bound for a query set Q in the systematic linear model if the set is not rigid. Okay, say now you take this matrix Q, and if you can write it as a sum of a low rank matrix plus a row sparse matrix, then I'll tell you how to get an efficient data structure from it. All you have to do here is store where you store these redundant bits to be a1 star through ar, inner products with a1 star through ar star with x, where a1 star through ar star form a basis of a. And then we know that to answer a query inner product of qi with x, all you need to know is the inner product of ai with x plus the inner product of bi with x. This sum of qi equal to ai plus bi you get from just the decomposition. Since we already, from the redundant bits, we already know the inner product of ai with x because we have stored the inner product with the basis, with all the points or vectors in the basis. And to actually answer or to compute bi times x, all you need to do is to like make t accesses because it's a t sparse vector. Okay. So this tells you that. So this already tells you that if you have a matrix that's not rigid, then you get efficient upper bounds. Okay, and also we prove the other direction also holds, and we get the equivalence that like if the set is RT rigid, then every systematic linear data structure with redundancy R must have query time
Sorry about that. It was
Good. Okay, so just to restate the result, what we show is that the set Q, if it's RT rigid, then every systematic linear data structure with redundancy R must have query time at least T. In pictures, all you have is, if for redundancy R, if the query time is at least T, then it implies RT rigid, and in the backward direction as well. Okay. Good. So here again we get that the best known systematic linear data structure load bonds are also of the same form, where T is at least n over R times log size of Q over R. Okay. And good. So any questions at this point about the result? Yeah.
Sorry, so how do you actually find the basis in which you take the inner products with, like on the previous slide?
Oh, if you just know the existence of A, then so we don't charge for the time to compute the basis or anything of that sort. So if Q is not rigid, then you know that this decomposition exists, and you know the matrix A exists, and hence you can and hence you know the basis. Yeah. So in this model, you don't charge the time to find A1 through AR star. Okay, good. So now 4 minutes. Okay, I have time. Yeah. Okay. So now so far I've been very abstract or vague about the set Q. Now I'm going to actually propose an explicit set, and then talk about what we know about it. Okay. So let's look at this vector matrix vector problem. So the goal is as input, you're given a square root n by square root n matrix M, and you'd like to compute the query is U transpose MV. So pictorially, what you have is M as input, and you have these vectors UV that you get as a query, and you'd like to output U transpose MV. And this is actually a linear problem, because this U transpose MV is nothing but the trace of two matrices, which is nothing but an inner product. Okay. So now in the systematic linear model, what we want is you want to be able to store R bits on the side, which are inner products of M with A1 through AR, and you access a subset of these redundant bits along with the entries of the matrix, and you'd like to compute this inner product. Okay. Good. So now for this for this data structure problem, you can associate a query set which corresponds to the set of all vectors that you get from rank 1 matrices of the form UV transpose. So look at UV that are like square root n length vectors. Look at UV transpose, which is square root n by square root n matrix. Now you take the square root n by square root n matrix and then make an n length vector by just unwrapping this whole matrix into a vector. Okay. Now if you look at this query set, which is a subset of f2 to the n, what we show is this is RT rigid, where T is at least n to the 1.5 over R. Okay. And here this again matches the best known rigidity bounds, and also the same result extends to the data structure problem as well, because we earlier showed that there's an equivalence between systematic linear data structures and rigidity. So we show that the query set corresponding to the vector matrix vector problem is rigid, and hence you also get the same lower bound for the data structure problem. Okay. Good. How much more time do I have? 2 minutes. Okay. Okay. So maybe I'll quickly tell you about linear data structures as well. So far we've been only talking about systematic linear data structures and nothing about the traditional cell probe model. So the question is, are there any connections to the traditional cell probe and whatnot? So let me just define quickly what the linear data structure model is. Here again, you have to store a vector x in f2 to the n, and you want to compute queries inner products of the form q times x. So instead of storing redundant bits on the side, here you are allowed to store 2n arbitrary inner products. Okay, and you get to access a subset of them to be able to answer the query. And the query time here is the number of accesses that you make to these 2n inner products that you store. Okay, and here for this problem, the best known lower bounds for explicit Q's query sets Q are again of the form log size of Q. Okay. And previously, Dvir, Golovnov, and Weinstein, they showed that if you prove a lower bound of omega of log size of Q times log n on the query time in this model, then you'll actually get semi-explicit rigid sets, with improved parameters. Okay, and in this work, what we show is that if you actually prove a lower bound of square root of log size of Q times n, then you get actually improved rigidity bounds just for the set Q, and it's also explicit. So the difference is that we want a stronger lower bound to be able to produce explicit rigid sets. They actually get semi-explicit rigid sets from a weaker lower bound. Okay, And yeah, let me just conclude with some open questions. The first question is this query set that corresponds to the rank 1 matrices actually seems very natural, and the proof of the lower bound for the rigidity is also like simple and follows from some basic linear algebraic facts. And the question is, can you improve that? Can you beat it? And the second question is if you can improve the explicitness guarantees in the work of DGW. And also for linear data structures, we are like stuck at like log size of Q for lower bounds, and like all previous works only tell you something or consequences to rigidity when you prove log size of Q times log n, or like square root of log size of Q times log n. But now, can you say something even like when you prove something slightly better than log size Q for linear data structures? Okay, yeah, I'll end the talk there. Thank you.
Any more questions?
Oh, I forgot to say, sorry. If you actually are not too sure about this rank 1 matrices, you can also look at a Reed-Muller code with square root and variables in degree 2, and then look at the corresponding generator matrix, and then that is also a potential candidate to actually prove better rigidity bounds for. Okay.
I had just one tiny question. When in the last data structure you presented, there was this A1 to A2n vectors. This 2n is just random number you put there, or?
Like it's just some constant times n. It doesn't matter. Like anything more than.
But it's constant times n. You don't.
Yeah, like it's constant times n is what I want. Yeah.
Okay.
Like you can also work with parameters as 1 plus epsilon times n, and then you get some trade-offs. But it's actually very clean, or the idea is already there if you just work with data structures that store 2n bits.
Okay.
Yeah.
Okay. Thanks.
Yeah. Thank you.
Okay, so the next speaker is Adam Polak, and he's going to tell us about joint work with Andrea Lincoln and Vassilevska Williams on monochromatic triangles, intermediate matrix products, and convolutions.
Good morning. So yeah, this is joint work with Andrea Lincoln and Vassilevska Williams from MIT. And don't worry if this title is a bit puzzling for you. I'll guide you through all the ingredients throughout my talk. So one of the things this talk is about matrix multiplication. You already heard a bit about it during the first two talks of this session. So just let me point out that the naive algorithm for multiplying 2n by n matrices runs in cubic time, and we know how to do it faster. We still don't know how to do it in quadratic time. Right now, improving even the 4th decimal digit seems very hard, but it is entirely possible that at some point we will be able to do it in n squared time. So matrix multiplication is kind of easy. But all these algorithms on this slide work only if we compute this product over a ring, namely we need subtraction. But sometimes we want to compute a matrix product over a different algebraic structure, and probably the most famous such structure is so-called tropical min plus semi-ring. And it is famous because it's runtime equivalent to computing for all pairs of nodes in a graph the length of the shortest path between these two nodes when the graph is weighted. And this product, of course, can be computed in cubic time, straight from the definition. And the best known algorithm so far is by Ray and Williams, and it shaves something from this cubic time. It's more than any constant number of logs, but it's not a polynomial improvement. It's still worse running time than n to the 2.99. And in fact, it's conjectured that it's impossible to solve a PSP substantially faster than cubic time. So on one hand, we have this easy regular matrix multiplication. On the other hand, we have this hard min plus product, which we believe cannot be solved much faster than cubic time. And quite surprisingly, oops. Okay, it's better. Quite surprisingly, there's a lot of problems in the middle. These are some matrix problems, some corresponding graph problems. And for all of these problems here, we know how to solve them in n to the omega plus 3 over 2 time. This is kind of in between the hard and easy case. It's roughly the average of these two running times. For some of the problems, we know small improvements using rectangular matrix multiplication. But the smaller the omega is, the smaller improvement. And if omega turn out to be 2, then these improvements vanish, and this running time becomes n to the 2.5. So that's why we coined the term intermediate matrix products for these problems. And all algorithms for these problems look at the top level very much the same. You run matrix multiplication several times, roughly square root n, to get some kind of approximate answer for dense part of your problem, and then you do something naive to get the rest of the problem solved. So a natural question would be, is it a coincidence? Is it a coincidence that we can solve all the problems in roughly the same time, and the algorithms look the same?
Are there any lower bounds for these other two problems?
You mean those in the middle?
Or the hard?
The hard is conjectured to be hard. So it's like...
But is there anything better than 2 n squared plus?
Is there any better lower bound for matrix multiplication?
For the min plus.
For the min plus, there is no better algorithm that is conjectured. I mean, there is no lower bound coming from another problem, but it's like the assumption. I mean, one of the three main assumptions in fine-grained complexity that a PSP cannot be solved faster than cubic time. Okay, so it would be tempting to prove some relations between these problems in the middle. Ideally, we would like to prove that all of them are equivalent, and this equal running time is not a coincidence. We are very far from it, but in this work, we provide some reductions in this area. I had word convolution on my first slide, and convolutions problem look pretty much similar. We have fast Fourier transform, which lets us solve the regular plus times convolution in near linear time. There is a hard min plus convolution, which is conjectured to require quadratic time, and it's equivalent to some variant of knapsack. And there is a bunch of intermediate problems, which all have algorithms running in n to the 1.5 time, and we have no idea if they are all equivalent or not. And this convolution world is kind of nicer than the matrix world, because we don't have an analog of if omega equals 2 statements. We already know how to solve the easy case in linear time, so everything is kind of simpler and cleaner. So in our paper, we give 9 reductions between these kind of problems. I don't have time even to state all these theorems formally, so instead of that, I'll give you 3 highlights, some selected results from the paper. So the first highlight is like the central problem of our chain of reductions. The problem we called all-edge monochromatic triangle. So you're given a clique with colored edges, and the task is to find out for each edge whether it belongs to a monochromatic triangle. Namely, a triangle such that all 3 edges have the same color. This is one of the intermediate graph problems or matrix problems. we can solve it in n to the omega plus 3 over 2 time, which would be n to the 2.5 if omega turned out to be 2. And this problem, there are two reductions involving this problem. One is that improving over this running time 2.5 is as easy as improving over triangle listing in sparse image graphs over m to the 4/3 time, which is currently the best known, assuming omega is 2. And on the other hand, it's as hard as refuting the three-sum hypothesis. And these running times are assuming omega equals 2. If omega is larger, some of these relations hold, but it's not that clean. So this is the first intermediate matrix product which has some lower bound, a lower bound based on three-sum hypothesis. So this was the first highlight. So we use this problem to give some reductions. We give reductions from unweighted APSP in directed graphs and all pairs LCA in directed acyclic graphs to monochromatic triangle. By using this roughly the same idea as we can give also reductions from these two problems to min-max product of two matrices. So this arrows means that if you can solve any of the lower problems in some time, you can solve the upper problems in roughly the same time up to poly log factors. And as I mentioned in the previous slide, this monochromatic triangle problem is sandwiched between three-sum and triangle listing. So this is the picture we have. Now I'll sketch the proof of this diagonal reduction from unweighted APSP to min-max to give you some flavor how our techniques look like. So we want to solve unweighted APSP using min-max product, log n calls to min-max product. So we define a matrix of shortest path up to length 2 to the I for each I. We'll proceed in log n rounds, increasing I. So the first matrix in this chain is just the input matrix. For each pair of vertices, you want to know if there is a path of length 1 or not, so if there is a match. The last one is the output, because if the graph is unweighted, then the length of the path cannot be larger than n. And now in a single round, we need to go from 2 to the I to 2 to the I plus 1. We do it separately for even paths and long and odd paths. And for even paths, if there is a path from U to V of length 2 to L, then there must be a vertex W, such that there is a path from U to W of length L, and from W to V of length L. And if this 2L is less than 2 to the I plus 1, then L is obviously less than 2 to the I. So we already have computed it. So basically, we compute the length of the shortest even path between U to V as a minimum over W of well, twice the max of U to W and W to V. So this is an upper bound, because twice maximum is less than sum, is larger than sum. And on the other hand, since there is such W, you can always find such W that there is equality. It's also a lower bound. So we can compute the even paths using the min-max product. For odd paths is kind of similar, but more technical, and taking the minimum of these two gives you the answer. End of the proof. And now the third highlight. So that was our picture. There's still no convolution in this picture, so let me add the convolution. So we defined an analog of monochromatic triangle in convolution world. This definition might look strange. If you thought about it for a while, it would make sense actually. The interesting thing is that, okay, so this is intermediate convolution problem. I should say that. You can solve it by running FFT squared n times for frequent values and then brute forcing the rest. And as you remember, the monochromatic triangle was sandwiched between threesome and triangle listing. So what are analogs in convolution world? So on one hand, improving over this 1.5 running time for monoconvolution is as hard as improving over quadratic time for threesome. So this is analogously the first convolution problem with a lower bound from some known hypothesis. And on the other hand, it's also as easy as improving over quadratic time from 3-sum. So this means that these two problems are equivalent. This is a fine-grained equivalence between problems of different running times. So even though the problems have the different running times, if you improve over one of them by a polynomial factor, you automatically improve over the other by a polynomial factor. Well, this is the first such non-equivalence, and for some reasons people believe that it might be hard to get a result of this kind. So we prove it's not the case. To sum up, this is how our full picture looks like. Thank you very much.
Questions? Okay, no questions. So let's thank the speaker. Okay, so the last talk of this session is going to be given by Nima Anari on joint work with Vijay Vazirani, showing that finding perfect matchings is as easy as deciding the existence of perfect matchings in the NC model.
All right, so this is joint work with Vijay Vazirani. So let me just jump into the problem. Okay, so the problem we want to study is finding perfect matchings in graphs. These are just sets of edges that have one edge incident per vertex. And the two natural questions that you can ask are a decision problem and a search problem, whether a given graph has a perfect matching, and the search problem is to just output one if one exists. So these are not exactly the problems we want to study. We want to study some slight variants of these, weighted versions. So in the weighted version, you're given weights on the edges of the graph, and the decision problem becomes whether there exists a perfect matching of weight at most W, or equivalently, you can think of what is the weight of the minimum weight perfect matching. And the search problem is if there is a perfect matching of weight at most W, output one, or equivalently output the minimum weight perfect matching. Okay. So the main result we show is that there is a very fast parallel deterministic reduction from the search problem to the decision problem in weighted graphs. Okay. So to be more precise, we only show this for graphs whose weights are polynomially bounded, or you can think of the input to the problem as being a graph whose weights are encoded in unary. Okay? So for this problem, we show a very fast parallel reduction from search to decision. So in the rest of the talk, I want to show you the context for why this is desirable and what this implies. And then in the last bit of the talk, I want to show you some ingredients of the algorithm. Okay? So for the perfect matching problem, there are roughly two categories of classic algorithms. So there are algorithms based on insights about the polyhedral aspects of perfect matchings. So these are roughly algorithms that move inside the convex hull of indicators of perfect matchings. You might have seen classic Blossom algorithms or augmenting path-based algorithms in bipartite graphs. So these are all things that deal with like structure of this convex hull of perfect matchings. And there is an alternative category of algorithms that are based on connections between the determinant and perfect matchings. So Lov'asz was the first person to devise such an algorithm. So roughly, if you're given a graph, you modify the adjacency matrix of this graph by replacing the ones with just symbolic variables or their negations. And then the determinant of this symbolic matrix would be 0 if and only if the graph doesn't have a perfect matching. So Lov'asz observed this fact and then basically devised an algorithm where you just replace the symbolic variables by random numbers and then test whether this determinant is 0 or not. And that would give you a very fast randomized algorithm to check whether a graph has a perfect matching. So these two categories of classic algorithms, they have pros and cons of their own. So the pros of the polyhedral algorithms is that they're deterministic, but the con is that they're sequential. You have to do one augmenting path at a time, or there are clever variants of that, but essentially you can't parallelize it very well. On the other hand, the determinant-based algorithms have this property that they're very efficiently parallelizable. You just have to compute determinants, and that's known to be very fast in the PRAM model. But the inherent con is that they're randomized. So you have to replace these symbolic variables by random inputs. Sometimes the random inputs don't work. Okay? So the main question is, can we have an algorithm that gets best of both worlds? Can you have a deterministic fast algorithm in the PRAM model? Okay? So we don't exactly know of such an algorithm in the NC model. So the NC model is you have polynomially many processors. You're allowed to run algorithms up to polylogarithmic time, and you want your algorithm to use no randomization. So we don't know of such an algorithm yet, so people have considered relaxations of this model. So the obvious relaxation is where you allow randomization, and this is the problem that was first solved by Lov'asz. The decision version, to be exact, was solved by Lov'asz. And then the search version was later solved by Karp, Upfall, and Wittgenstein, and followed by another slicker proof by Mulmuli, Vazirani, and Vazirani. So there is another relaxation of the NC model that has gained popularity in recent years. That's the quasi-NC model. So this is a relaxation where you allow more processors. Okay? So instead of polynomially many processors, you allow quasi-polynomially many processors. So in this version, the first breakthrough was by Fenner, Gurger, and Theorem, who showed that both decision and search can be solved in this quasi-NC model. And this was generalized to general graphs by Svensson and Tarnowski. Okay? So what I want to talk about today is a third relaxation of this NC model. It's called pseudo-deterministic NC. So a pseudo-deterministic algorithm is a notion that was introduced by Gatt and Goldwasser in 2011. So roughly what it says is that you're allowed to use randomization, but the output should be unique, a unique function of the input with very high probability. Okay? So it's almost trivial that for decision problems, this notion doesn't make any difference because the output can either be yes or no. But for search problems, the fact that the output has to be unique with very high probability is a non-trivial requirement. Okay? So Goldwasser and Grossman showed that you can solve the perfect matching problem in bipartite graphs in pseudo-deterministic NC. And what our result does is generalizes this to general graphs, non-bipartite graphs. Okay? So the reason is we have a reduction from search to decision that doesn't use any randomization. And for decision problems, you can just repeat them arbitrarily many times to lower the failure probability. And therefore, unless any of your calls to the decision oracle fails, your algorithm outputs the unique solution that it has to output. Okay? So another corollary of our results is for another relaxation of the problem. So in this relaxation, you don't relax the computation model. You want the algorithm to be in NC, but you relax the inputs to the problem. So you only pay attention to specific classes of graphs. Okay? So there are many known classes of graphs where the decision problem can be solved in NC. This is because you can actually count the number of perfect matchings in NC. So you can trivially also see whether there is a perfect matching or not by just seeing whether the count is 0 or not. So one famous case of this was planar graphs. So prior to our work, we and also Sankovsky showed that for planar graphs, there are NC algorithms. So there are slightly more general classes of graphs called K333 graphs. For those, you can also count the number of perfect matchings. But our result generalizes this to, to a more general class of graphs of genus at most log n. So for this, prior work had shown how to count the number of perfect matchings, but we didn't know how to output a perfect matching in NC. All right, so in the remaining time, I just want to say a few bits and pieces of the algorithm. So the main notion that we use in the algorithm is that of a matching minor. So this observation goes back to Edmonds, who considered the convex hull of all indicators of perfect matchings of a graph, the perfect matching polytope, and showed that this convex hull is described by a set of linear inequalities that you see. So the first set of linear inequalities is trivial. It's saying that if you have a perfect matching, there must be one edge adjacent to every vertex. The second one is also trivial. It's just saying that the fraction of times you've taken an edge should be a non-negative number if you're looking at a point inside the convex hull. The third one, which is the non-obvious one, is that if you have an odd set of vertices, there must be at least one edge going out of that odd set of vertices. So this is obviously true for every perfect matching and also for every convex combination of them. And the surprising fact is that these are the only inequalities you need. These are the inequalities completely describing the polytope. Okay? So now if you're looking for a minimum weight perfect matching, you're looking at a face of this polytope. And a face of this polytope is described by setting some of these linear inequalities to linear equalities. Okay? So some of the edges, you have to set them to be equal to 0. And some of the odd sets, you have to make the sum of the edges going out of that odd set be equal to 1. Okay? So if you're looking at a face of the matching polytope, that's just described by a set of disallowed edges and a bunch of tight odd sets. And this observation, again, goes back to Edmonds, that whenever you have a tight odd set, you can sort of reduce the size of your graph, you reduce the size of your problem by contracting that odd set. Okay? This is because every perfect matching was having at most one edge going out of this odd set. So in the contracted graph, that perfect matching also has one edge adjacent to that contracted vertex. Okay? So one thing that you can do is you can choose a weight function and then get a reduction in your input size by removing a bunch of edges and also contracting pieces of the graph. Then you have to again solve the minimum weight perfect matching problem in the new graph. Okay? So this is roughly the outline of the algorithm. What we do is we carefully go through a crafted list of weight functions. Each one of them defines a face of the matching polytope. We find the tight odd sets and disallowed edges describing that face of the polytope. And that gives us a simpler graph. We just choose amongst all possible graphs that are formed from this process, we choose one that has the minimum number of edges, and then we recursively apply this process. Until we get to roughly a constant size graph, there you can just choose a perfect matching arbitrarily. Now this perfect matching is just for the contracted graph, but you can extend that to a perfect matching by looking inside each of the contracted pieces and recursively applying this. Okay? So there are some questions about this algorithm. One is, how do you find disallowed edges and tight odd sets that describe the face of a polytope? And disallowed edges, you can just find them by making queries to the decision oracle. You can see whether that edge, if you put a very small weight on it, whether that can be part of a perfect matching or not. And for tight odd sets, it was already which is the more complicated case. This was already solved by Saigen, Gabo, and Sankovsky for us. Okay. So the key technical contribution of this work is showing that there exists a family of Palmilli many weight functions such that for all graphs, for at least one of these weight functions, this algorithm removes a 1/polylog n fraction. Okay. Yeah, let me just skip these. Yeah. So So yeah, so for dense graphs, we show that you can find a bunch of edge disjoint cycles, linearly many edge disjoint cycles, and for any of these cycles, one of the edges is going to be either disallowed or contracted. For sparse graphs, we do something else. And that's all I'm going to say about the algorithm. So let me just conclude. So what I showed you was an NC reduction from search to decision for weighted graphs. A corollary of this was a pseudo-deterministic search algorithm, and also an NC search algorithm for special families of graphs where you can count. So one obvious question is, can you make this reduction work for unweighted graphs? We don't know the answer to this. So another question is, what about simple variants of the perfect matching problem where the polyhedral approaches don't work? So this algorithm that I showed you was a blend of the polyhedral approach and the determinant-based algorithms. But there are very simple variants of the perfect matching problem. One of the famous ones is exact matching, where we don't know of polyhedral algorithms. So the problem, let me just mention it. You have a graph, and you've colored the edges into two colors, red and blue, and you want to see whether there exists a perfect matching with exactly k many blue edges. Okay? So all of the polyhedral algorithms we know for perfect matching just crumble under this slight variation. Thank you.
There's a question?
Yeah.
Why doesn't the weighted result imply the unweighted result?
So our reduction is to the weighted decision problem. That's the.
Oh, I see. Okay.
We query. Even for unweighted graphs, we query weighted graphs.
And you want to say one more thing about that? I had a similar question, which is, can you say something about why this is so much harder? So is it because
so the heart of it goes back to this this result, which I only mentioned in passing. So finding these tight odd sets, the algorithm by Saigon, Gabo, and Sankovsky. So that's a very non-trivial piece of this whole algorithm, and so if you can make that work for unweighted graphs, that will the rest of it will go through for unweighted case as well. But yeah, I don't think I have enough time to go through the details of this algorithm. Yeah.
There's one last question. Yeah.
So this part also. So the part you just mentioned, does that also depend on choosing these weight functions?
The part that I mentioned?
Yeah, does the tight out sets part also depend on crafting these weight functions?
No. So this result exactly says if you give me any weight function, then it can find a set of odd sets that describe the face corresponding to that weight function. By just making queries to the decision oracle.
Okay, so let's thank Nima and all the speakers of the morning session.